Okay, in this video I would like to discuss the quadratic formula. This is something you might have run into previously, but we're going to go over it again in case it's been a little while for you. Okay, the quadratic formula applies to finding the solutions to a quadratic equation in standard form. Okay, so if you remember our discussions from the previous video, a quadratic equation in standard form has the quadratic form set to 0. Okay, so you've got 0 on one side, and then you've got ax squared plus bx plus c on the other. And a, b, and c are constants, as you know. A is assumably not 0, otherwise it wouldn't be a quadratic. Okay, and somehow you want to find out what the values of x that would satisfy that equation. Now, last time we talked about completing the square, so what we're going to do is actually complete the square in complete generality to solve this problem, and the result will be what we call the quadratic formula. Okay, so let's go ahead and let's write our equation again. So we've got ax squared plus bx plus c equals 0. Do you remember the first step was to what? Isolate the x squared terms on the left-hand side. So here I'm going to subtract c on both sides, and this reduces to ax squared plus bx equals negative c. Okay, so that's equivalent to our original equation, but I've only got x terms over on the left there. Now, a is not 0, so I can divide on both sides by a, and that's exactly what I'm going to do, okay? Because when I divide on both sides by a, the quadratic on the left-hand side is going to end up being monic. In other words, the leading coefficient on, or the coefficient on x squared will be 1. Okay? All right? So you can see that holds here. I would have a over a x squared plus b over a x, okay, equals negative c over a. Okay, so that's our new equation here. And we like that being monic here because we can play our little completing the square trick. Now remember, when you've got a monic quadratic there, to complete the square, you take the coefficient on the x term, and in this case, what do I have a negative there? I'm spacing out. Okay, that's actually positive. Not that it makes any difference in the end, though. Okay, but I would have what? B over a divided by 2, okay, which is actually b over 2a, right? Because when you're dividing by 2, it's like multiplying by half. B over a times a half is b over 2a. Okay, remember we have to square that quantity, so we actually get what? B squared over 4a squared. Now that's the magic number I want to add to this guy up here to make that a perfect square over on the left-hand side, okay? So that's what I do. I add b squared over 4a squared on each side. Now, because this is a negative c over a over on the right-hand side, I actually write it this way. Rather than negative c over a plus b squared over 4a squared, I actually wrote the b squared over 4a squared first, so then I'm just subtracting c over a. Okay? And then there's the left-hand side. Okay? Now the left-hand side should be a perfect square, we said, from our completing the square technique here. And in fact it is. It's x plus b over 2a quantity squared. Okay? And you can verify that if you wish by just actually foiling this out here. Okay? And on this side here, I've got these two fractions, so what I'm going to do is combine them into a single fraction by getting a common denominator. You can see this denominator is 4a squared, and this denominator is a. The least common denominator is, in fact, the 4a squared, so I don't change the first fraction. It has the denominator I want. The second fraction, I want that a to become a 4a squared, so I need to multiply in the numerator and denominator by 4a to get an equivalent fraction with 4a squared down in the bottom. Okay, so I get minus 4ac over 4a squared, and then I can combine those two fractions because they have a common denominator. And it's b squared minus 4ac all over 4a squared. Okay? And now you guys know the technique where we take what? The square roots, right, of each side and get rid of absolute values. So we get x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac all over 4a squared. Now remember that square root is applying to both the numerator and denominator. So what I really have here is x plus b over 2a equals plus or minus the square root of the numerator, so the square root of b squared minus 4ac, over the square root of the denominator, which is, now you guys remember yesterday, let me throw in one little thing here. The square root of 4a squared, technically, remember yesterday I showed, or in the last video I showed, that this would be what? Well, the square root of 4 is 2. The square root of a squared is not a, it's absolute value of a. Okay, so you should say, maybe technically I should have the absolute value around the a there. Well, that makes no difference in the end because of what? Because of that plus minus in the front. I think it's easy to convince yourself if I have the plus or minus the absolute value of a, or any number, okay, or plus or minus a, I get exactly the same two set of values. Do you see that this gives me exactly the same two set of values? Plus or minus a versus plus or minus the absolute value of a. Okay, it's the same set of numbers, so there's no point in retaining those absolute values in this case. Okay? All right, almost my last step here, my penultimate step, is to add negative b over 2a on each side, isolating the x over on the left-hand side, so that we have x equals negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a, or over 2a. When I add these two together, notice that they've got a common denominator, so voila, we're there. X is negative b plus or minus the square root of b squared minus 4ac all over 2a, okay? Now, when I say that, I like to say all over 2a because some students have a tendency in the quadratic formula to shorten their division so that the 2a is only dividing the square root. Okay, you can see that that is false from the above. The 2a is dividing the first term in the numerator as well, so you got to stretch that division symbol all the way out here. Okay? Now, I would like you to memorize this if you don't have it memorized already. So you should put it on a flashcard or something and write it a bunch of times, and you should get it and have it in your memory. Okay? So you have it at your fingertips here. Let's take a few concrete examples here. Let's solve this quadratic equation. X squared minus x minus 1 is equal to 0. Okay, we just have to read off the parameters. A equals 1, B equals negative 1, and C equals negative 1, and plug those into the formula right up here, okay? So we get what? Negative B would be negative 1 plus or minus the negative 1 squared. Notice the necessity for the parentheses on the square. Minus 4AC all over 2A, okay? Now you just work out the arithmetic. That's actually 1 plus or minus the square root of 5 over 2. You can get your calculator and get a couple approximations there to as many decimal places as you wish. Okay, so there's the solutions. Okay, let's have a different question here. Find the x-intercepts of the parabola. This should be y equals. Okay, y equals x squared plus 4x minus 7. Okay, well, how do you find the y-intercepts? Well, you would go back and do what? Set it equal to 0, okay? So I make y equal to 0 so that I have a 0 there, okay? Now it's a quadratic equation in standard form with the leading coefficient being a equals 1, b equals 4, c equals negative 7. So negative b would be negative 4, and then you go plus or minus the square root of 4 squared minus 4, a, which is 1, c, which is negative 7, and the whole thing divided by 2 times a, So that's 2 times 1. Now, do you do the arithmetic here? I think I got it right. I got negative 4 plus or minus the square root of 16 plus 28, which is 44. Okay, now you notice I can, in the square root there, I can actually factor out the square root of 4. The square root of 4 is 2, so I've got actually 2 square root of 11 there instead of the square root of 44. Then I've got negative 4 plus minus the square root of 2, square root of 11 all over 2. Remember that 2 is dividing both terms. Negative 4 divided by 2 is negative 2. And the 2 divided by the 2 there is 1. So we've got 1 times the square root of 11, or the square root of 11. So we've got negative 2 plus or minus the square root of 11. Okay, so you can see, like we did last time in the previous video, finding x-intercepts of a parabola corresponds to doing what? Solving a quadratic equation. Let's do one more here. Let's find the x-intercepts of the parabola y equals f of x equals x squared minus 2x plus 5. Again, a is equal to 1, b is negative 2, and c is equal to 5. Let's plug them into the formula. Negative b would be negative negative 2 plus or minus b squared, so that would be negative 2 squared minus 4. AC would be 1 and 5, all over 2 times 1 for the 2a. And that is 2 plus or minus 4 minus 20, which is negative 16, all over 2, which is 2 plus or minus the square, well, square root of 16 is 4, right? So I factored out the 4 times the square root of negative 1 over 2, and then I divide the 2 into both terms there. I get 1 plus or minus 4 over 2, which is 2 square root of 1. Okay, now hold on a minute. There is no real number which is the square root of negative 1, right? All right, I was proceeding very formally here. There is no such thing for us now as what? The square root of negative 1. Any real number squared, positive, negative, or 0, is non-negative, right? So how could there be any real number whose square is negative 1, right? And that's what we would mean by the square root of negative 1. Some number whose square is negative 1. There is no such real number. What does this indicate about the parabola? It indicates that the parabola has no x-intercepts, okay? It has no x-intercepts, okay? Now, let's come here just to see this more clearly. You could graph this if you want, but a quick thing to do here, I took a problem where it's really easy to complete the square on it. This is actually x minus 1 squared plus 4. Okay, so that's what our function is, x minus 1 squared plus 4. Now you know that the vertex then would correspond to what? 1 comma 4. Okay, so you could see 1 comma 4. Imagine that as a point in the xy plane. But the leading coefficient is 1. 1 is a positive number, so it opens upwards. It's smiling, right? So you've got a parabola that looks like this. Well, it looks better than that. But it's opening upwards, and it has a point which would have to be a minimum point as far as y values go, right? It would have to be a minimum point at 1 comma 4. Okay, so the smallest value this function could ever attain as far as the y values go is 4, and that would occur when x is equal to 1. Okay, but the x-axis has what? The x-axis is actually where y is equal to 0. So you could see here this parabola couldn't possibly intersect the x-axis, right? It couldn't intersect the x-axis. That's another way of looking at this. But the idea is, if you're looking for x-intercepts of a parabola and you get what? Something other than a real number for your solution, like a square root of a negative number, then you know the parabola has no x-intercepts. You do not have to do this second part. I'm just doing that to reiterate the point that this particular parabola has no x-intercepts, okay? Now, one reason I took this problem last here is because in the next video, I'm going to just start discussing something called the imaginary and complex numbers, in which we introduce this concept of negative 1. Now that's going to be a totally different type of number. It's going to be what we call an imaginary number, okay? It has nothing to, okay, so it's outside the real number system. The square root of -1 does not appear in the regular Cartesian xy plane, okay? But that's, you might have run into those type of numbers before, but we're going to be discussing them in depth in the next video. Okay, well, memorize that quadratic formula and do the problems I give you, and you should be in good shape. Okay, I hope you understood all that.